So we start today with section 4.2, where we are going to be using some probability rules. And it starts to get a little tricky here, so stay with me. And if any questions come up, make sure you get a hold of me and get your questions answered. So we start off with an example. And the example says, suppose you roll 2 dice. So these are going to be, 6-sided fair dice. What is the probability that you get a 3 on each die? So we could write this something like probability 3, 3. So think about the first one. When you roll that first die, what is the probability you get a 3? And it's going to be 1 out of 6, right? 1 out of 6. There's 6 sides. One of those sides is a 3 on it. So when you roll the next die, does the fact that you got a 3 on the first one have any bearing on the probability of getting a 3 on the second one? And of course it doesn't. We'll see later they're said to be independent events. So because you get a 3 on the first one doesn't make it less likely that you'll get another 3, right? The probabilities completely start over again, and it's going to be 1 out of 6. And what we're going to do is multiply here. So we're going to get a 3 on the first one and also a 3 on the second one. We're going to just multiply these probabilities. And when we do that, we get 1 out of 36. Now remember, quick review here, when you multiply fractions, you go straight across, right? 1 times 1 is 1. 6 times 6 is 36. And what we're doing right here, we're multiplying these two, and we're doing that because of what's called the multiplication rule. So we'll talk about that rule in a little bit, but basically we're going to keep multiplying these probabilities. So example 2, when you start, this one's going to be a little different. We've got 5 red marbles, 2 blue marbles, and 1 green marble in a bag. We're going to take 2 marbles at random from the bag without replacing the first marble before taking the second. So we're not going to replace it. So this is called sampling without replacement. So just to make a little picture here. So here's what we've got. We've got 5 red, 2 blue, 1 green. And they want to know, what's the probability that the first marble is red and the second marble is blue? Okay, so think about this. We're going to pick the first marble. There's 5 red, 2 blue, and 1 green, right? 5 red, 2 blue, and 1 green. So if we just pick a marble, what's the probability we're going to pick a red marble out of here? Well, there's 5 red marbles, and there's 8 marbles altogether, right? Yeah, 8 altogether. 5 of them are red, so the probability we pick a red marble is 5 out of 8. So it would go 5 out of 8. Now, it says without replacement, so we're going to pick another marble, but this red one we're not going to put back. So now we don't have 5 red marbles anymore. Now we have 4 red marbles, right? Without replacement, we're not putting it back. And now we're going to pick again, and we want to know what's the probability that we get a blue marble. Well, now we've got 7 marbles, right? There's 7 marbles left. 2 of them are blue. So the probability we pick a blue marble is 2 out of 7. And again, what we're going to do is multiply. So just like before, when you multiply fractions, you go straight across. And you can cancel first. Typically when we're taught multiplying by fractions, we can cross cancel. But I'll just stick to going straight across. 5 times 2 is 10. 8 times 7 is 56. And you can reduce that if you want. I'm just going to concentrate on getting the answers for right now. So I'll just go 10 over 56, and you can reduce if you'd like. So again, what we did here is we're multiplying, and we're using that same rule. Although we haven't really talked about it yet, I'm just kind of getting us set up for it. This is also what we're using is the multiplication rule. Okay, so then we've got example 3. This example is sort of like example 2 above, but this time we're going to replace the marble. So we have, the same initial setup. We've got these marbles here. We've got 5 red, 2 blue, 1 green. And this is called sampling with replacement. So it's the same question. What's the probability that the first marble is red and the second marble is blue? So just looking at this, with this initial setup here, the probability that you pick a red marble is going to be 5 out of 8, just like before. Now the difference is now we replace it. We put the red marble back in the pile, randomly pick another one, and the probability that we pick a blue one now is going to be 2 out of 8. So now we're going to multiply again by 2 out of 8, and we get 10 out of 64. And once again, we're multiplying because of what is called the multiplication rule. So one thing you'll notice that when we replace the marble, all the original probabilities are restored. Whereas here, the original probabilities had been changed when we didn't replace it. And a concept that's going to be important for us is this concept of events being independent. So we've got a definition here. 2 events are independent if the occurrence or non-occurrence of one event does not change the probability that the other event will occur. So, got a note here, not replacing the first marble in example 2 changes the remaining probabilities, so these events are not independent. They are said to be dependent. So we've got this multiplication rule for independent events, and it says this: the probability of A and B, in other words, the probability of event A and event B both happening, if they're independent, we can just take the probabilities of each event and multiply them together. So probability of A and B, which means they both happen. If they're independent, it's just the probability of A times the probability of B. And this extends indefinitely. So if you have 3 events, A and B and C, you just multiply all 3 of them together. So as an example of this, suppose you roll a die. So it's going to be, remember, 6-sided die, and then flip a coin. Are these events independent? Well, you have to ask yourself, when I roll this 6-sided die, is that going to somehow affect my coin flip? And it won't, right? They're completely independent. So are these events independent? Yes, they are. And since they are independent, I can just figure out the probability of each of them happening, right? And then multiply them together. So this probability of a 5 and then an H, I put the comma here, but we could have put 5 and H. Same sort of thing though. So if we want to figure out the probability of rolling a die and getting a 5 and then flipping a coin and getting heads, we just consider them one at a time. The probability of rolling a 6-sided die and getting a 5 is 1 out of 6. The probability of flipping a coin and getting heads is 1 out of 2. Since they're independent events, I just multiply them together and we get 1 out of 12. Now notice what we're doing. We're finding the probability of this. So our answer has to be, I'm just going to recall something we talked about before that's really important. Recall the probability of any event or combination of events has to be between 0 and 1. So if we're asking for the probability of something, the answer is going to be between 0 and 1, right? And of course, if you write it as percents, it's 0% and 100%. So if the events are dependent, in other words, not independent, then one event causes a change in the probability of the other. So now we look and we've got some other multiplication rules. These are only called multiplication rules because in the formulas we have to multiply these probabilities. The multiplication rules are really going to be used whenever we have an AND. So we have a probability of A and B. Whenever we have these and, like both events have to happen, then we use this multiplication rule. So we're going to see there are 3 of these rules, and they take a little practice. And I'm going to give you a handout, chapter 4 handout, and then you can always use that. And when you're doing the homework problems, if they have the handout with you, you can kind of narrow down which ones of these formulas to use. And I'll show you how that works when we work on some of the homework problems together in this video. So first we have to know about what this new notation is. So this right here, this probability of A and B, and then we've got this probability of A times the probability of B given A. So we need to talk about what that means. But notice this is for independent or dependent. The rule above this was just for independent events, but this works for dependent or independent. So here's what we need to know. We need to know this new, what this means with this vertical line here. So this means the probability of A given B. So let's first just write that down. This is the probability of event A given event B. That means the probability that A happens given that B already happened. Right? It's the probability of A given B. So if events A and B are independent, then of course they don't change each other's probability. So think about this. If A and B are independent, they have nothing to do with each other, like rain in Topeka. Let's say event A is I'm going to eat lunch tomorrow, and B is it rained in Topeka. The probability of you eating lunch tomorrow, given that it rained in Topeka, isn't that just the probability of you eating lunch tomorrow? In other words, the fact that it rained in Topeka had no bearing on whether or not you eat lunch tomorrow, right? Which means these events are independent. So if events A and B are independent, they're independent from one another, they don't influence each other's probabilities. If they're independent, then they don't change each other's probabilities. So the probability of A given that B happened, it's just the probability of A. The fact that B happens has no bearing on A, right? It's like rain in Topeka. It's not going to affect us. So same thing here. The probability that B happens given that A happened, well, they're independent. The fact that A happened had no bearing on B, so it's probability of B. So one thing to note when you read this is the probability of A happening, right? Probability of A happening given that B happened. But it's the probability that A happened, right? So whichever one comes first, that's the one we're looking at. So this says the probability of B happening given that A happened. So what we're saying here is that if A and B are independent, then this is equivalent to this, and this is equivalent to this, because they're independent, they have no influence on each other. So then if we were to use, let's say we look at this one here. So the probability of A and B happening, and we know this form that works for everything, independent or dependent, but I'm going to show that both of these formulas collapse into the above formula if they are independent. So let's say A and B are independent, and we're going to use this formula. If A and B are independent, then the probability of A happening given that B happened is just probability that A happened, right? Right here, we could swap this out with this. And if we do that, we get the above formula, because if we get rid of probability of A given B and we replace it with probability of A, then this is just probability of B times probability of A, which is the formula we had above. Right, so these formulas here are more general. They work for independent or dependent, because if the events are independent, then these formulas will just collapse into the formula above. And that'll make more sense when we're actually doing some of these problems. So if you're not with that 100%, just hang on. When we do the problems, formulas are much easier when you apply them to a problem. So basically, these are the general rules, but when the events are independent, then we can swap these out, and then these will turn into that other formula, which said probability of A and B is probability of A times probability of B. So we've got one more. There's a conditional probability formula. And the way that we do these conditional probability problems, we won't actually have to use this formula, but I'll show you it anyway. So we've got this equation here, and it says solve this equation for probability of A given B. In other words, we want to isolate this, right? We want to get this thing by itself. So just think of the good old days in algebra class, and we could say, well, I can get rid of probability of B by dividing this by probability of B, as long as I do the same thing to the other side. So that would cancel, and that would leave us with probability of A and B over probability of B equals probability of A given B. Right? And that's what we were looking for. So I guess we could just reverse this and write probability of A given B is equal to the probability of A and B over the probability of B. So if you want to find conditional probability directly, you can do this. You can use this formula. The probability of A given B equals this. Now in the problems when we have to do this, I'll show you another way to do it where we don't actually need the formula. So for example 5, let's look at page 169, number 2. Or basically it's section 4.2, problem number 2. And it says if two events A and B are independent, so A and B are independent, and it says that the probability of A is 0.3. It says, what is the value of probability of A given B? So see if you can figure that one out. It's almost a trick question. So take a minute, see if you can figure it out, and then come on back. Okay, so hopefully when you're figuring that out, you got 0.3. So here's the reasoning. Because it says right here they're independent, so they have no bearing on each other's probabilities. So if the probability of A is 0.3, then probability of A given B is still going to be 0.3, right? They're independent. The fact that B happened had no bearing on it, right? So if the probability of you going through the McDonald's drive-thru today is 30%, the probability of you going through the McDonald's drive-thru, given that it rained in Topeka, still 30%, right? They have nothing to do with each other, independent. So it's almost like a trick question sometimes, it seems like, but it's the fact that they're independent means that the probability of A given that B happened is just the probability of A, 0.3. So this independence question is an important one for us, so we need to have some ways to tell when events are independent. So let's take a look at this. A couple of ways to do this. So first we could say if the probability of A given B is just the probability of A, or the probability of B given A is just the probability of B, then events A and B are independent. You can see it here, right? The probability of A given B is just the probability of A. The fact that B happened didn't change the probability of A. And same thing here. The probability of B given that A happened, it's just the probability of B. So the fact that A happened had no bearing on the probability of B happening. So when that happens, we could say A and B are independent. So if either of these are true, then we can say A and B are independent. We could also go from the definition. So the definition of independent says events A and B are independent if and only if the probability of A and B is probability of A times the probability of B. And this is, in math, you'll see if and only if, IFF. And it's what's called a biconditional. It means it can be read in both directions. So as an example of that, we've got this, it's the only example I can think of right offhand. It is kind of a bad example, but if you have a conditional statement, which is normally what we have in English, we'll say something like this. This is a conditional statement. If it rains, I will take an umbrella. So this goes in one direction. It's conditional. If it rains, then I will take an umbrella. So I can't reverse it. It's not biconditional. I can't say, if I take an umbrella, it will rain. Right? I can't say that. So it's conditional. Here's the reason why I don't like this example. Although it's getting better. I don't hear it as loudly, but I used to, every single time I would say this, every time I'd say this word umbrella, in my brain I would hear umbrella, Ella, Ella. So hopefully that doesn't happen to you from that song that tortured me every time I did this example. So this, just when you see this, it means that you can switch these around. So if probability of A and B equals probability of A times probability of B, then events A and B are independent. So for this test of independence, we could check three things, either this or this or this. And if any one of them are true, then these events are independent. So we don't need to check all three. We just need to see if one of them works. If one of them works, then the events are independent. It's really, after this, it makes it sound really difficult and tricky. It's really not. This is like, technically, this is what's happening, but it's going to be easier than that. So you'll see when we do some of the problems. So for example 6, we are once again talking about this multiplication rule. And here we're just going to see that it really extends indefinitely. It can extend to more than 2 events. It could be 3 events, 7 events, 10 events, however many events there are. So this is, suppose there are 3 engines working to run a generator to provide backup power during a power outage. Assume that engine failures are independent. So in other words, these engines have their own fuel sources, so they're completely independent of one another. And the probability of any one engine failing is 0.1. 0.1, or 1 out of 10, right? Or 10%. So what is the probability of all 3 engines failing? So in other words, what is the probability of fail, 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 or the first one fails and the second one fails and the third one fails? And engine failures are independent. So since they're independent, basically we can just multiply all of these together. This is a really bad probability, by the way. 10% chance of engine failure. That's really bad. But if we multiply these all together, which we can do because of the multiplication rule, you 0.001. Sometimes people call this rule the multiplication rule, sometimes the multiplication principle. It's the same thing, though. And then we've got, anyway, just to be clear, so this is just saying that this thing can be extended to more than just 2 events. Here's 3 events. If there were 5 engines all independent, we just put all 5 of them in here, multiply them together. And now we're going to look at a Venn diagram to show the difference between and or. So when you have the events A and B, here's event A, here's event B, and the and is this overlap. It's a lot like in geometry you'd have an intersection. It's very similar. So the event A and B. This means that both events happen. So when you talk about A and B both happening, we're talking about this overlap here. Both events happen. When we talk about A or B, well, in math, we always use the inclusive or. Inclusive or means A or B or both. In English, we almost always use the exclusive or, like you are a freshman or a sophomore, right? But when we say you're a freshman or a sophomore, we don't mean you're a freshman or a sophomore or both, right? We mean exclusive or. But in math, we generally when we say or in math, we mean inclusive or, which means one or the other or both. So A or B, if this is event A and this is event B, A or B is all of this together. And that means that one event or the other event or both events happen. That's why the formulas are different. When there's and, we use these multiplication formulas that we've seen, or the multiplication rules. When there's an or, we're going to use what's called the addition rules, and that's what we're going to look at next. So I'll just let me add that. Here we use the multiplication. For this event, we would use the multiplication rule. For this event, we would use an addition rule. And the Chapter 4 handout will have all those rules all in one spot. And I'll show you, when we get done with the notes here, we're going to work on quite a few of them in the book for 4.2 on this video. And then I'll show you how to refer to the Chapter 4 handout to pick out which rule we need to use. Because that's a little bit of a tricky part in 4.2. So here we have these addition rules, and when there's an addition rule involved, we've got an or. With the multiplication rule, we've got an and, but the addition rules involve or, it's a jack, probability of a jack or a queen, and they involve addition. So consider a 52 card shuffled deck. So we've got clubs, right? Spades, hearts, and diamonds, right? So just a quick review so this problem makes sense. So there are 4 suits. Each suit has 13 cards, right? So 13 times 4 gives us our 52. So we're going to consider 52 card shuffle deck. We're going to pick one card, and we want to know what is the probability that we get a jack or a queen. Probability jack or queen. Well, what if we just wanted to figure out the probability of getting a jack? Well, there's a jack of diamonds, jack of hearts, jack of spades, jack of clubs. So there's 4 jacks altogether, right? 4 jacks out of 52. So that would be 4 out of 52. And then what about if I add the probability of getting a queen? Well, what's the probability of getting a queen? Well, again, there's a queen of diamonds, queen of hearts, queen of spades, and queen of clubs. So there's 4 queens. So what we could do is this. We could say the probability of getting a jack is 4 out of 52. We could add that to the probability of getting a queen, which is 4 out of 52. And we would get 8 out of 52. Or if you wanted to reduce it, you could to 2 out of 13. And you can, when it comes to probabilities, you can leave it like this, you can reduce it, or you can use a decimal. But if you use a decimal, make sure you round correctly, right? Wherever you decide to round, make sure you round correctly at that spot. So here's what's happening in this case. This is really easy to see if I do a quick Venn diagram. So we've got jacks here, queens here, no overlap, right? 4 cards here, 4 cards here. There is no overlap. There is no card that is both a jack and a queen. So when there's no overlap, we can just add these together. These are said to be mutually exclusive, which we'll talk about in a minute. Well, let's talk about it right now. Okay, these are called mutually exclusive or sometimes they're called disjoint. What that means is they cannot both happen. We cannot pick one card and get a jack and a queen, right? It's got to be a jack or a queen. So since there's no overlap, there's no card that falls into jack category and queen category. They're called mutually exclusive, which means they cannot both happen. If I pick one card, I can't get both of these. I can get one or the other, right? Jack or queen, these are called mutually exclusive. And when you have mutually exclusive events, the addition rule for OR is really easy. We just figure out the probability of getting this, figure out the probability of getting that, and we add them together. Okay, but what about this one? Now we want to figure out the probability of getting a 10 or a heart. So for this one, we could do probability of 10 plus probability of heart. I'm going to leave it at this for now. So what's the probability of getting a 10? Well, again, there's a 10 of clubs, 10 of spades, 10 of hearts, 10 of diamonds, right? So we're going to say that's going to be 4 out of 52. What about the probability of getting a heart? Well, 1/4 of all the cards are hearts, right? There's 13 hearts in a deck, so that's going to be plus 13 out of 52. But if we just add these, we're going to make a mistake, because isn't it true that one of these cards is a 10 of hearts, right? One of these 10s is a 10 of hearts. And then over here, one of these hearts is also a 10 of hearts. So we're counting the 10 of hearts twice. So here's what we've got in this case. We've got our Venn diagram. And we've got hearts here. There's 13 of these. And then 10s. That's a very bad circle, but the fact is there's an overlap here, right? This 10 of hearts belongs to both of these. The 10 of hearts is in the heart group, and the 10 of hearts is also in the 10. So we basically counted it twice here. So what we have to do is subtract out one of them. So the formula, we have to subtract out the probability of getting a 10 and a heart. So we want to count the 10 of hearts, but we don't want to count it twice, so we have to subtract this off. So this formula is a little bit longer. And now we go minus. Just think, what's the probability of drawing one card and getting a 10 and a heart? Now, in other words, a 10 of hearts. There's only one 10 of heart. So we're going to subtract off 1 out of 52. And when we do that, we get 16 out of 52, or 4 out of 13. And the difference between these two is this one is not mutually exclusive. The reason it's not mutually exclusive is there is a 10 of hearts here and also here, right? So that 10 of hearts we counted twice. So if we're going to figure out the OR, probability of something or something else, we need to know if these things are mutually exclusive or not. If they are mutually exclusive, we just add them. But if they are not mutually exclusive, when we add these together, we're going to be double counting, because the 10 of hearts is in this group and the 10 of hearts is also in this group. So we counted it twice here. So then we subtract this off to make that correction. Okay, so not only do we have to be concerned with independence, but we also have to be concerned with whether or not things are mutually exclusive. So we've got a definition here. Two events are mutually exclusive or disjoint if they cannot occur together. So events A and B are mutually exclusive if the probability of A and B is 0. So here's something mutually exclusive. Let's say, what's the probability of you being taller than 6 feet and shorter than 6 feet? It's 0, right? You can't be taller than 6 feet and also be shorter than 6 feet. Those events are mutually exclusive. So if the probability of two events both happening is 0, in other words, these two events will never happen together because the probability of them happening is 0, then these events are mutually exclusive. So we've got this addition rule for any events. And again, an addition rule just means you've got an or question. So this works for any events at all. The probability of A or B is the probability of A plus the probability of B minus the overlap, probability of A and B. Now this works for any of them because remember that if A and B are mutually exclusive, then the probability of A and B is 0. So if they are mutually exclusive, this is 0, so you could kind of like get rid of this, which is why it says, so we have the addition rule for mutually exclusive events is just a shorter version of this. All right, so here's the general rule. This is the addition rule for any events. If these events happen to be mutually exclusive, then you have the shorter version, because if they are mutually exclusive, the probability of A and B is 0. So you can just cover that up, get rid of it, and it simplifies to this. So there's two addition rules. Really, there's just one. You could always use this one. You know, just this will be 0 if the events are mutually exclusive. But if you know they're mutually exclusive, you can just go right here. And then there's a little note here, which says if A and B are mutually exclusive, and we know that event A happened, then we also know that event B did not happen. Right? Because they are mutually exclusive, they cannot both happen. So if you know that event A did happen, then you also know that event B did not happen. And then there's a little note here, and this happens sometimes in this chapter. We just have to be careful about independent events and mutually exclusive events. So independent events, I always think of rain in Topeka. If I flip a coin and it rains in Topeka, is that going to have any bearing on my coin flip at GRCC? No, they're no bearing at all, so they're independent. Mutually exclusive just means they cannot both happen. So independence means that the outcome of one event does not influence the outcome of the other. Mutually exclusive means that if one event occurs, then the other cannot occur, which clearly means that they are not independent, right? Because if one happens, that means the other doesn't happen, which is the very opposite of independence. So just be careful with these two. Just kind of keep in mind they're different ideas, right? Independent events and mutually exclusive events are different things. So there is this chapter 4 handout that you have. It's in Blackboard under the handouts tab. And we're going to refer to this handout as we do the homework problems. We're going to do a few homework problems together here so you can get the hang of these. So you're going to need this chapter 4 sheet. It's got, if you look at it, it's got some rules here for independent events, mutually exclusive. Really, the main thing that we're going to need when you use this is this right here. We're going to need the multiplication rules and the addition rules. Those are going to be the most important things. Well, when you're working on 4.2 homework, you want to just be able to have access to these rules right here. Then we've got this conditional probability rule. On the back, we've got rules for section 4.3, which we'll talk about later. But for right now, for 4.2, just go ahead and make sure you have this this sheet here. Okay, so make sure you get to the handouts tab on Blackboard and get yourself a copy of the chapter 4 handout. And then we can work on some of these problems. So this is from section 4.2. This is number 4B. And I'm going to show you how to make sense of these formulas. So 4B says, it's got some givens. It says given the probability of A equals 0.7. Let me mention one thing too. There's a kind of an easy mistake to make when you start. You don't want to do this. This doesn't make any sense. This is what this literally says. The probability of event 0.7. It sounds like a scary event, right? The probability of event 0.7. That sounds terrible. Were you here when the event 0.7 happened? So we don't want that. That doesn't make any sense. This is what we want. The probability of event A is equal to 0.7. So definitely don't write that kind of thing. So, all right, let's just erase that completely so we never even have it in our memory. All right, so for 4B, it tells us the probability of A is 0.7. It tells us that the probability of B is 0.4. And B says, so we've got another given. It says the probability of A and B equals 0.2. So this is what's given for 4B. And then it says compute probability of A or B. Okay, so here's what we have to do. Here's how you want to approach these problems. We want to look over at our handout sheet. And so let's move this over here. So we've got an OR question, right? So that's what we want to think about. They are asking us for the probability of A or B. So you want to go over here to the ORs. You've got two formulas for OR. We can use this one if events A and B are mutually exclusive. So to see if they're mutually exclusive, I have to make sure I don't cover everything. Well, let's take a look at what we've got here. The probability of A and B is 0.2. This means that A and B can both happen, right? Probability of A and B. There's a 20% chance that they both happen, which means they are definitely not mutually exclusive. If this said probability of A and B is 0, meaning they can't both happen, then they would be mutually exclusive. But because they can both happen, then they are not mutually exclusive. A and B can both happen. There's a 20% chance of that. So we know we're not here, which means we can basically just cross this one off the list, and we have to use this one. So to answer this question, probability of A or B, I'm using this. So I'm going to say, well, it is the probability of A plus the probability of B. You don't really need to write this step. I'm just doing it just so we know exactly what we're doing. Minus, whoops, put something there I didn't want to write. So minus the probability of A and B. So let me fill in the blanks. Probability of A is 0.7. Probability of B is 0.4. Now think if, just for a second, think if I would have chosen this one, how would I know that something went wrong here? So when I add this, I'm going to get 1.1. Is that even possible to have a probability of something being 1.1? And it's not, right? Probability of no matter what you put in here, when you figure out the probability, it's got to be between 0 and 1. It can't be 1.1. So kind of keep an eye out for that. If you use the wrong formula, sometimes you'll know because you get an answer that can't be true. So I need to subtract off the probability of A and B, which is 0.2, and then that gives us our 0.9 for 4B. So basically, the thing to look at is what are they asking, and the ones that will give the most trouble are the ors and the ands. So just first thing, look, okay, it's an or, so I'm down here, right? I've got to use one of these. If it's an and, I'm going to be up here, okay? So let's try another one. So number 6 starts off and it says the probability of event A is 0.7, the probability of event B is 0.8, and for part A it says A and B are independent. So whatever these events are, they're independent from one another, which means that they have no influence over each other's probabilities, right? They're completely independent of one another. And they want us to figure out the probability of A and B. So again, focus when you first start on what they're asking. It's an and question, the probability of A and B. So it's an and question, which means we are right over here. These are the multiplication rules. And we just have to go through and pick out which one we need in this case. Now this one, they made it kind of easy for us. They told us right off the bat A and B are independent. So when we look at the and, we got this independent one. So we want to use this one, and it's set up. We're pretty much good to go. They're saying if events A and B are independent events, then use this one. So that's one that we want. So we want to just, the probability of A and B is the probability of A times the probability of B. So again, I'll put this step in here that you don't really need to put, but just so we know what we're doing. And we fill in the blanks. It's going to be 0.7 times 0.8. Remember, don't do this kind of weird stuff, right? When you do this, your instructor has a very sad face because that doesn't make any sense. So we don't want to do that. Don't make your instructor sad, maybe even crying. We don't want that. So we go back here and we multiply. 0.7 times 0.8 gives us 0.56. And again, just to check, what number should we expect to get here? Something between 0 and 1, right? Which we got, 0.56. Okay, so A, they made it kind of easy for us. They just told us, well, these are independent. So we kind of knew what to do, right? So a lot of times it won't be quite as obvious. Okay, so for part B, we still have this. These are still given. Okay, but now we're on part B. So in addition to this, we also have this. The probability of A given B is 0.1. And they want us to figure out what is the probability of A and B. Well, think about this. Again, they're asking us an and question. So we need to look over here at the ands. And this is the easiest one is this last one. So let's just see, are events A and B independent? Well, we have to look up here. So for 6, it says, oh, you know what? 6B, I wrote this wrong. This says, okay, let me fix what 6B says. Okay, I think I was looking at a different problem here. Okay, so 6B says the probability of B given A is 0.9. Okay, sorry about that. So we still have this. This is still good. This is from number 6. And now 6B adds this. So now we have, I'll just put this too. So we have this other fact that we know. So we know these 3 things, these 2 things, and this 3rd thing. So probability of A and B, well, it's nice if they're independent because we can just use this easy one. So let's see if A and B are independent. Well, to do that, we need to look up here and see that the probability of B happening is 0.8. Right, 80% chance of B happening. But look at this. The probability of B happening given that A happened, this is a straight up vertical line here. The probability of B given that A happened is 0.9. So something about A, when A happens, it makes B more likely, right? This is the probability of B given that A happened, 0.9. Probability of B by itself, 0.8, which means that these are not independent, right? When A happens, it makes B more likely to happen. So A and B are connected some way. They're not independent. So when we look down here at our and rules, we can get rid of this one. It's not going to work. So it leaves us with these other 2. So what happens here is both of these will work. They'll both work, but normally we only have enough information to use one of them. So looking at what we know, one of these we're probably not going to be able to use. And if you look closely, you'll see that the second one won't work for us. The second one requires us to know the probability of A given B, which we don't know. We know the probability of B given A. So we can really cross that one off too. And that leaves us with just this one. So the probability of A and B is going to be the probability of A times the probability of B given A. So every time you have one of these AND questions, you just look through here and try to pick the one that you can use. So once we figure out the one we can use, the probability of A is 0.7. Probability of B given A is 0.9. Multiply these together and get 0.63. Okay, so again, just have these with you when you do your homework, and you're basically going to be using these two sections here, depending on whether it's an and or an or. Okay, got another problem for us. This is problem number 8. And there's been variations of this one on tests in the past, and they always give us trouble. Not the part A question, the part B question. So make sure you're with me on this one, and if not, make sure you get a hold of me and ask me about it. So for problem number 8, they say the probability of A complement is 0.8, probability of B is 0.3, probability of B given A is 0.2. And part A says compute the probability of A and B. So right away, first thing I notice is an and question, which sends me over to the and, which means I need to use one of these three formulas. For every and question, we're going to use one of these three. And normally what we do is we just eliminate a couple of them, and the one we're left with we go with. So usually I look for this. I just look and see, okay, are A and B independent? Because if they are, we can just use this last one, which is kind of the easiest one to use. So A and B are independent. So to check, we can check that really easy with this given information. The probability of event B, the probability that that happens is 0.3. The probability that event B happens given that A happened, now it's only 0.2. So these are not independent. The fact that A happened made B less likely to happen, right? Because on its own, the probability of event B, 0.3. Probability of event B, given that event A happened, 0.2. So they're not independent, right? So we cannot use this one. So that means, let's see, so we can cross this one off the list. So we've got these other two left. So now they'll both work, but normally we won't have enough information to use one of them. Now right now it looks like we don't have enough information to use either one, but what about this? The probability of A complement is 0.8. So that actually implies something about the probability of A, right? If the probability of A not happening is 0.8, what's the probability of A happening? 0.2, right? So they indirectly give us the probability of A happening. They just don't write it out here. So with that, now we've got everything for this first one, right? We don't know the probability of A given B, so I can get rid of that one. But now we're ready to go. This is going to be the probability of A times probability of B given A. The probability of A is 0.2. Probability of B given A is 0.2, which gives us 0.04, right? 0.2 times 0.2 is 0.04. Remember, be careful. We have to move the decimal point over twice total, so you get 0.04 here. So the probability of A and B happening, not a real high probability, but there's about a 4% chance, right? Probability of A and B, 0.04. Okay, so we did okay on that one. When we had this version of a question on a test, we were pretty good on this, but here's where we got messed up. Part B for 8 says, compute the probability of A or B. This is what gave us trouble. Well, first thing again, we've got an OR question. So I am going to look down here at the ORs, right? It's going to be one of these two formulas. So if events A and B are mutually exclusive, so remember, mutually exclusive means that they cannot both happen together. That means the probability of A and B is 0. Well, we found something right here in part A. Probability of A and B is not 0, right? The probability of A and B is 0.4. So I can't use this bottom one. I have to use the top one. So what we need for this is going to be the probability of A plus the probability of B minus any overlap that we've now counted twice. So we subtract it off once. This is what we kept forgetting on the test. Everybody's pretty good here, but A and B are not mutually exclusive. We know that because of what we found in part A. Based on this information, the probability of A and B is 0.04. It's not 0. It's 0.04. So A and B can both happen. So we need to put this in here. So then we get the probability of A, which is 0.2, plus the probability of B, which is 0.3, minus probability of A and B, which is 0.04, which gives us a total of 0.46. And always remember, when you get your answer, always check and make sure it's between 0 and 1, which it is. So let's try one more of these. Number 20. Again, this is section 4.2. Number 20 says, you roll 2 fair dice, a green one and a red one. And they ask us about probabilities. And sometimes a picture helps on these. So there is a picture of the overhead view of all the possible outcomes of rolling 2 dice. It's on page 157. And sometimes seeing that picture makes these a little easier. You don't have to see the picture, but it's sometimes helpful. So if you want to take a look at it, it's on page 157. You don't really need to, though, to do the problem. But number 20 says, what is the probability of getting a sum of 7? Number 20A. So probability of, let's just say a sum of 7. Well, one way you can think of this I think is kind of an easy way, is just think about, with our problem, we've got a green die and a red die. And we're going to roll these. And to get a sum of 7, well, it could be that we had a 1 on the green and a 6 on the red. Just think of all the ways that we could get a sum of 7. So it could be a 2 and a 5, a 3 and a 4, 4 and a 3, 5 and a 2 and a 6, and a 1. Right? So like this represents a 3 on the green die, a 4 on the red die. This is really it. This is the only way we can get a sum of 7, by rolling these 2 dice. So looking at this, how many ways are there? 1, 2, 3, 4, 5, 6 ways. There are 6 ways to get a 7. Then we just have to think, well, how many outcomes are there altogether if you roll 2 dice? This is where this picture will make it much easier, because you can see, looking at the pictures, 36 different outcomes. You can kind of see it if you think of, well, each, like for the green, this 1 has 6 outcomes for the red, and this 2 will have 6 outcomes, and the 3 will have 6 outcomes. So altogether, we've got 6 times 6, or 36 total outcomes, right? For rolling 2 dice, there's 36 total outcomes. You can see all 36 of those on page 157. But the fact that there's 36 total outcomes means the probability that you get a 7 is going to be 6 out of 36, because there's 36 total outcomes. 6 of these have a sum of 7. Right, so it's going to be 1 out of 6. Or 6 out of 36, or 1 out of 6 if you prefer, if you simplify it. So then 20b says, what's the probability of getting a sum of 11? Probability of getting 11. Well, I'm going to do the same way here, the green and the red. There's not as many choices. You could get a 5 and a 6, or 6 and a 5. And that's it, really, right? Because we need to get sum of 11, and it's a 6-sided die. That's the only way we can go. There's only 2 choices. And again, there are 36 total outcomes. Remember, because if you roll a 1 on the green, you could have 6 different outcomes on the red, 1 through 6. If you roll a 2 on the green, you get another 6 outcomes on the red, 1 through 6. If you go all the way down the line, all the way to 6 on the green, you get another 6 outcomes. So there's 36 altogether. Or look at this picture to make it easier. But the probability that you get a sum of 11 is just going to be 2 out of 36, or 1 out of 18. Then part C gets a little tricky. What is the probability of getting a sum of 7 or 11? So C says probability of 7 or 11, the key being an or question. And it says, are these outcomes mutually exclusive? Well, the question is, can I roll these 2 dice and get a 7 and also get an 11? That would be a neat trick, right? So you can get a 7 or 11, you can't get both. So these are mutually exclusive, right? If I roll 2 dice, I can't get a 7 and also get an 11, right? I can get one or the other, but I can't get both, so they are mutually exclusive. So if you look on the handout for the or, when they're mutually exclusive, I can just add these together. There is no overlap. So probability of a 7, so this time I'm going to keep them not reduced, since we're going to have to add these together. And you get 8 out of 36, which would be 4 out of 18, or 2 out of 9, or as a decimal if you want to. Okay, so that should get you started in 4.2. Make sure you have your formula sheet near you. 4.2 is a little challenging, so really give these a good attempt. They may take a little longer, but just keep grinding away at them, and let me know if you have any questions.